11.39, or let's say 729 over 64. And the point is that this is less than 13, which is equal to the left-hand side. So it also holds for n equals 7. Okay, so my basis, to be clear, is the cases n equals 6 and n equals 7. The reason I'm doing two basis cases is because when I do the inductive step, I'm going to need to use two previous cases. Okay, inductive hypothesis, I'm going to let n be at least 7 because the last basis case I did was 7. And suppose that the claim is true, meaning like f of k is bigger than or equal to 3 over 2 to the k minus 1 for all k between 6, which is my smallest basis case, and n. Okay, so we're assuming that the claim is true for k equals 6, k equals 7, blah, 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 up to the case k equals n. And now we're going to use this to prove the n plus 1 case. Okay, so in my inductive step, what we want to prove is that fn plus 1 is at least 3 over 2 to the n plus 1 minus 1, which is the same thing as 3 over 2 to the n. Notice here I wrote the words we want to prove, and then I wrote what we want to prove. That's okay to start your inductive step. Don't start your inductive step by just writing this. F of n plus 1 being, is at least 3 over 2 to the n, because that's what you want to prove. But if you start your proof by writing that, it kind of looks like you're assuming it's already true. And so you definitely shouldn't just write this and then kind of manipulate both sides or something, because that's not going to be good. But you can write, we want to prove this, because that's clear. It's clear what you mean. To do this, so we're going to just start by looking at the left-hand side, which is fn plus 1. So by the definition of the Fibonacci numbers, fn plus 1 is fn plus fn minus 1, right? Because every Fibonacci number is just the sum of the two previous Fibonacci numbers. Okay. I think once you've gotten to this point, it's kind of clear what to do, because I've broken down fn plus 1 in terms of two previous values of the sequence. And what I know is that every previous value of the sequence, by my inductive hypothesis, satisfies a certain inequality, so I can just plug in that inequality. So what I mean is that f of n, or fn, we can write as being at least 3 over 2 to the n minus 1. And fn minus 1 is at least 3 over 2 to the n minus 1 minus 1. Okay? Because that's just me applying the inductive hypothesis with k equals n and with k equals n minus 1. Okay, so here I have to say by IH, otherwise you will lose marks. You've got to say why these things are true, right? Justify your steps. And now it's just some kind of clever algebra. So I'm going to take this, I'm going to factor out, so both of these terms have like a 3 over 2 to the n minus 2 in them. And when I factor that out, from the first term I'm left with a 3 over 2. From the second I have a 1. Okay, so all I've done is factor this out from both terms. Okay. And this is the same as 5 over 2 times 3 over 2 to the n minus 2. At this point, you might be like kind of stuck because, I mean, we kind of want 3 over 2 to the n, and we don't have it, right? This is not 3 over 2 to the n, but the good thing is that it's even bigger than 3 over 2 to the n, right? So I can rewrite this as 10 over 4 times 3 over 2 to the n minus 2. And the thing is, 10 is bigger than 9, so this is like bigger than 9 over 4 to the 3 over 2, or sorry, times 3 over 2 to the n minus 2, which kind of magically, 9 over 4 is the same as 3 over 2 squared, which is all just equal to 3 over 2 to the n, which is exactly what we wanted. Okay, so that does the inductive step, and then we have to remember the conclusion, which is just basically repeat what you've proved. So basically all we say is that fn is at least 3 over 2 to the n minus 1 for all n at least 6. Okay. So the clever part there was really, and this is kind of a common thing in these inequality questions, the tricky part is figuring out what you've got and what you need to get to in the end, and knowing precisely how much you can throw away. So here the tricky part is going really from this step, from 10 over 4 down to 9 over 4. But if you think about where you're trying to get to, and maybe you can do some kind of rough work on the side, right? So I didn't do any rough work here, but you could just say, if you were doing some rough work, you could look at, just to see if your approach is going to work, you could take 5 over 2, 3 over 2 to the n minus 2, and you want this to be bigger than 3 over 2 to the n, and then if you kind of simplify this a bit, like, you'll be able to see that that it's definitely true, but now it's slightly difficult to kind of bring this back and see exactly how to do it. But yeah, hopefully once you see it, it's clear, and if you practice enough of these, I think it gets easier. Okay, let's move on to another induction. So we want to prove that if I sum up things like 1 times 2 plus 2 times 3 plus 3 times 4 ... up to plus n times n plus 1, it gives you n times n plus 1 times n plus 2 over 3. Okay, let's do the basis. So again, this is by induction. Again, this is from chapter 4. So consider the case n equals 1. We've got left-hand side is just 1 times 2, which is 2. Right-hand side is just 1 times 1 plus 1 times 1 plus 2 over 3, which also evaluates to 2. So left-hand side equals right-hand side. Therefore, it is true for n equals 1. Inductive hypothesis. So this time we actually can just do this by weak induction. Last time we kind of needed strong induction somehow. But yeah, so this time let's just say, so let n be at least 1 and assume that 1 times 2 plus 2 times 3 plus ... up to n times n plus 1 is equal to n times n plus 1 times n plus 2 over 3. Now note that in my inductive hypothesis, it's important like what this sentence is saying. So I'm only assuming this is true for one value of n. Your inductive hypothesis absolutely should not say, assume that this thing is true for all n, right? Because that would be assuming what you're trying to prove, which is a big problem. Okay, so let's now do the inductive step. So basically we want to prove this thing for n plus 1. So we want to show that 1 times 2 plus 2 times 3 plus dot dot dot. I'll write n times n plus 1 and then n plus 1 times n plus 2. So this is the same thing as we have above, except with n plus 1 in the place of n, right? And we want to show this is n equal to n plus 1, n plus 2, n plus 3 over 3, which is what you would get by plugging in an n plus 1 in for n. Okay, so yeah, this is kind of a standard thing. So, right, by the inductive hypothesis, I can deal with almost all of this sum, right, and just replace it with this thingy over here, right? Because that's what my inductive hypothesis says. It says that this sum is equal to this. And the sum I'm dealing with in the inductive step is the same sum, except with an extra term. But yeah, so by the inductive hypothesis, the left-hand side can be replaced by n times n plus 1 times n plus 2 over 3 plus this n plus 1, n plus 2. Okay, and now at this point it's just some algebra. So put this on the same denominator, n times n plus 1 times n plus 2 plus 3 n plus 1, n plus 2, all over 3. And now you might be tempted to just multiply this all out and then collect stuff and try to factor it, but that's going to be really, really ugly. Don't do that. Just look at this thing. We can factor out an n plus 1 and an n plus 2, right? So both terms have a common n plus 1 and an n plus 2. We can pull out from both of them. And then you're left with an n plus 3, because an n from here and a 3 from there. It's all divided by 3. But now look, this is exactly what we wanted to prove. So this is equal to the right-hand side. And so we're done. Okay, so, well, we're not completely done, because don't forget to write your conclusion, otherwise you're going to lose marks. So 1 times 2 plus 2 times 3 plus dot 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 up to n times n plus 1 is equal to n times n plus 1 times n plus 2 over 3 for all n at least 1. So as usual, the conclusion is just rewrite what you were supposed to prove. Okay. So I was also asked to solve 4.19, chapter 4, question 19. I'm not going to do it because this is just one of your ICA questions, so there's already a solution there. So it's the solution to, so if you want to see how to prove this one, check out the solution to ICA number 10. Okay, one more. Let's prove that 4 to the n minus 1 is always a multiple of 3. for all n at least 0. Now, the hint is pretty useful here. But anyway, let's do this by induction. This is again from chapter 4. The basis is the case n equals 0. So consider n equals 0. Then what is 4 to the 0 minus 1? Well, anything to the 0 is 1. So we've got 1 minus 1, which is 0. And 0 is a multiple of 3, right? So I'll say which is a multiple of 3 because 3 times 0 equals 0. Okay. Inductive hypothesis, let's just use weak induction. So let n be at least 0, and suppose that 4 to the n minus 1 is a multiple of 3. Inductive step, consider 4 to the n plus 1 minus 1. And now we should probably look at this hint, right? So it says that if I take, let's say 4 to the k minus 1, it doesn't matter if it's a k or an n or whatever, right? If you have 4 to the k minus 1, it's equal to 3 times 4 to the k plus 4 to the k minus 1. So let's apply this hint. So 4 to the n plus 1 minus 1 is 3 times 4 to the n plus 4 to the n minus 1. And like, you can see why this is true if you kind of do some algebra and stuff, but you can also just say perhaps by the hint in this case, because that's what the hint tells you. And now here's the thing. By induction, we know that this is a multiple of 3. And this thing here is just clearly a multiple of 3. And if you add two multiples of 3, you're going to get a multiple of 3. So basically by the IH, 4 to the n minus 1 is equal to 3k for some k in the integers, right? So by the inductive hypothesis says that 4 to the n minus 1 is a multiple of 3. What does that mean? It means it's equal to 3 times k for some k. So if I take 3, so I'm going to go back to this expression here. So 3 times 4 to the n plus 4 to the n minus 1 is equal to 3 times 4 to the n plus 3 times k, which we can then collect up, pull out a 3. So it's 3 times 4 to the n plus k, which is a multiple of 3 because 4 to the n plus k is an integer. Okay, so conclusion, we just restate what we proved. 4 to the n minus 1 is a multiple of 3 for any n at least 0. Okay, so yeah, that's the end of this video. Feel free to send more questions.